Hello, dear colleagues. My name is 72 from NTNU non-mechanical lab. Today, I will give a presentation with the title "Determine Materials Equivalent Structure Curve with axisymmetric rotated tensile specimen." Before the presentation, I will introduce the co-authors. Dr. Xiaowen, who works in the same type of industry, Norway, and Professor Jin He and Professor Zhilian Zhang works in the non-mechanical lab, Norway. The presentation consists of 5 sections. First, I will give a short introduction about the background and the definitions, and then we'll give 3 words about the Bridgman correction. In the following, I will introduce the method we proposed, and later I will introduce the experimental and numerical verification of the proposed method. This presentation will be ended with conclusions. Tensile test is usually performed to determine materials equivalent materials structuring curve. Usually we use smooth round bar specimen or smooth specimen with rectangular cross section. From a tensile test we can get an engineering structuring curve and true structuring curve. For the smooth round bar specimen, the engineering stress is calculated by dividing the load by the initial specimen cross-section error, and the true stress is calculated by dividing load by the current minimum cross-section error. For the engineering stress, it will go up with the increase of strain, and will go down when the diffuse necking happens. While for the true structuring curve, it will goes up with the increase of strain. And before diffuse necking, the deformation on the specimen is uniform, and the true stress we calculate with this equation is exactly the material's equivalent stress. And but after diffuse necking happens, the triaxial stress state will happen in the root region. In that case, the distribution of the equivalent stress strain curve, the distribution of the equivalent stress looks like this form. While the true stress we calculate with this equation looks like this. Now, in this case, the true stress after diffuse necking cannot represent the material's equivalent stress and need to be corrected. And many methods have been proposed based on the triaxiality correction. And among them, one is the most famous is the method proposed by Bridgman. And for his method, the correction factor is a function of the ratio of A and R. A is the minimum cross-section radius, and R is the Roche couch radius. Although this method is widely used, however, this method may not be accurate sometimes for different materials. And the gap between the Bridgman corrected stress and the material's equivalent stress sometimes may be very high. For example, in this paper, Nanosa and colleagues performed experimental and numerical analysis for this D98 materials, and they found out that the Bridgman corrected equivalent stress, the gap between the Bridgman corrected stress and the input stress is very large, and the error can be reached up to 10% when the strain is around 1.3. For the Bridgman correction method, we need to measure A and R. A can be measured accurately, but R sometimes is very difficult to determine accurately. And the Bridgman correction method is not very accurate sometimes. For example, in this figure, and also this Bridgman correction method is mainly for the homogeneous material. It is not suitable for the cross-wire specimen due to the inhomogeneous environment and the unpredictable fractalization. So we are thinking, is it possible to obtain the equivalent stress strain curve directly without applying the Bridgman correction method? Our strategy looks like this. We assume that the material follow a stress strain law, and we use this material to the lost specimen. And from numerical analysis, we obtain the true stretching curve. And with our method, the true stretching curve from the lost specimen can be converted back to the input equivalent stretching curve. We run numerical analysis with this axisymmetric model, and we assume that the material follows this power law hardening rule. And the yield stress of this material is 400 megapascal. And the hardening exponent n here ranges from 0 to 0.2. For n equal to 0, this material represents a perfectly plastic material. And the logic geometry here is calculated by the ratio of A0 or R0. A0 is the minimum cross-section radius, and R0 is the initial logic culture radius. And the ratio ranges from 0.25 to 3. And from the numerical analysis, we obtained the true stress strain from the logic specimen. Here in this figure, I presented the results for the perfectly plastic material. We can see the true stress here from the logic specimen is normalized by the yield stress. And we can see that for this true stretching curves, for the specimen, for the logic specimen with the ratio of A0 over R0 smaller than 2, the stress goes up. The true stress goes up with the increase of strain. While for the ratio of A0 over R0 equal to 3, the true stress goes down with the increase of strain. And we are thinking this is due to the logic. And the ratio between the true stress and the input equivalent stress is calculated by this equation at a given strain. And here, for the logic geometry with A0 over R0 equal to 3, the ratio are presented for all the hardening exponent we analyzed. And we can see that for these 5 curves, it behaves. It has the same behavior. And if we take the value corresponding strain equal to 0.8 as a reference, all the data on this curve is normalized by the value. And after the normalization, we can see that these 5 curves in this figure all map into one, and which can be fitted by a linear equation. Note that for this equation, it works for all the hardening exponents, which means that this equation is hardening independent. And the ratio now can be expressed as the reference value and the G equation, the G function. And for all the reference value we taken here is plotted in this figure of the function of the hardening exponent. We can see that for different logic geometries, this reference value also has the same behavior. And if we take the value for the perfectly plastic material as a reference, and all the data on this curve is normalized by the value for the perfectly plastic material, we can see that in this figure, after the normalization, this curve in this figure classified into one, which can be fitted by a second order polynomial function. And now the reference value can be written as Fn, which we call is the hardening function, and the reference value for the perfectly plastic material. Now, if we insert this equation into this function, we can have this equation. Now Fn is a hardening represent the hardening of the material, while G function is related to the geometry of the logic specimen and the deformation of the specimen. And if the calculation of this term and the G function will return back to the linear fit for the perfectly plastic material. And here B1 is the slope for the linear fitting for this curves, and B2 is the intersection for these curves. And the B1 and the B2 for the perfectly plastic material is then fitted as a second order polynomial function of the A0 or R0. Now we have this equation. With this equation, we can convert the two stress from notched specimen to the material's equivalent stress strain curve. Here we presented a numerical verification. In these two figures, the notch geometry of the notched specimen is A0 or R0 equal to 1.25. And in this figure, the hard exponent is n equal to 0, which is the perfectly plastic material. And we can see that the corrected stress strain curve show good agreement with the input equivalent stress strain curve. It should be noted that for most correction methods, it does not work for the perfectly plastic material, and our method works. And also for the hardening exponent equal to 0.125, we can also find a very good agreement. And in our analysis, we also performed the analysis for hardening exponent as high as n equal to 0.35, which we also get satisfied results. And we also verified this method by performing tensile test with smooth round bar specimen and the notched specimen. And pay attention. For this test, we use a so-called edge tracing method. With this method, we can capture the deformation of the specimen during the test, and also we can ensure the minimum cross-section diameter accurately. And here in this figure, I presented the engineering stress of this stress strain curve from this test. And from this test, the strain corresponding to the maximum engineering stress is regarded as the material's strain hardening exponent. And for what is the notched specimen, we can say that the strain corresponding to the maximum yield stress is almost the same. And the two stress and from the notched specimen and the smooth round bar specimen are presented in this figure. With our now we have this notch geometry parameters. We have the hardening exponent. We have the strain. With our proposed method, the two stress from notched specimen are corrected, and the results are presented in this figure. We can see that the red curve is the equivalent stress corrected by the Bridgman correction, while the other curves are corrected by the proposed method. We can see that these curves show good agreement before strain. When the strain is smaller than 0.5. After that, the equivalent stress strain curve is slightly smaller than the Bridgman correction method. And for all the curves we corrected from different notch geometries, we can obtain the identical equivalent stress strain curve, which is the material's equivalent stress strain curve. And here comes the conclusion. First, a new tensile testing method is proposed to determine material's equivalent stress strain curve with notched specimens. And secondly, the proposed method has been verified numerically and experimentally. And the last one, since the deformation of the proposed specimen is localized in the notch region, the new method can be used for determining the equivalent stress strain curve of each individual zone of environment. Thanks for your attention.